talked about so far is what the derivative of f tells us about the graph. It tells us the critical points, where the function is increasing and decreasing, and the local minimums and maximums of our function. What we want to talk about next is what the second derivative tells us about the function. So take a look at these two graphs. Both of them connect the points A and B. The shape is just a little bit different between the two of them. Notice that the tangent lines on the first one are below the graph, and the tangent lines of the second one are above the graph. We call the first one concave upward and the second concave downward. So just the definition of each of those. Concave upward is when the graph of f lies above all of its tangents on an interval I, and concave downward is when the graph of f lies below all of its tangents on I. See if you can pick out which intervals are concave up and concave down. From A to B, it is concave upward. From B to C, it is concave downward. From C to D, it is concave up. D to E is down, E to P is down, and P to Q is up. Now let's look at what happens at those points where they change. If you look underneath the picture, there is a definition of an inflection point. An inflection point is a point on a curve where it changes from concave up to concave down. So looking at the same graph, which points do you think are inflection points? Let's see. At B, it looks like it changes from concave up to concave down. At C, it looks like it changes from concave down to concave up. At D, it looks like it changes from up to down. And at P, it looks like it changes from down to up. So what does this tell us about the second derivative? How is this going to help us any? Well, we have a concavity test. If the second derivative is greater than 0 for all x and I, then the graph is concave upward on I. If f double prime of x is less than 0 for all x and I, then the graph of f is concave downward on I. All right, let's try an example. You might want to write this down. Sketch a possible graph of a function f that has the following. F prime of x is greater than 0 on negative infinity to 1. F prime of x is less than 0 on 1 to infinity. F double prime of x is greater than 0 on negative infinity to negative 2 and 2 to infinity. And f double prime of x is less than 0 on negative 2, 2. The last part is the limit of f of x as x approaches negative infinity is negative 2, and the limit as x approaches infinity of f of x is 0. All right, let's look at what part A tells us. Part A tells us that f is increasing on negative infinity to 1 and decreasing on 1 to infinity. B tells us that f is concave up on negative 1 to negative infinity to negative 2 and 2 to infinity, and concave down on negative 2, 2. And part C tells us that there are horizontal asymptotes, one at y equals negative 2 and one at y equals 0. The first thing we should do is draw horizontal asymptotes. So we know that y equals x minus 2 is a horizontal asymptote. And we know that y equals 0 is a horizontal asymptote, which is just our x-axis. We know at negative 2 it has to change from concave up to concave down. And we also know that at positive 2 it changes from concave up to concave down. From part A, we also know where the function needs to be increasing and decreasing. So if we draw this graph through these points, it should look something like this. Now we want to talk about the second derivative test. Last chapter we talked about the first derivative test. Now we want to talk about the second derivative test. Suppose f double prime is continuous near C. If f prime of C is 0 and f double prime of C is greater than 0, then f has a local minimum at C. If f prime of C equals 0 and f double prime of C is less than 0, then f has a local maximum at C. And remember, when the derivative equals 0, that is a critical point. Okay, let's look at an example. If we have the function f of x equals x to the fourth minus 4x cubed, let's find the concavity, the points of inflection, the local maximum and minimum, and sketch the curve. The first thing we'll need is the derivative. When we take the derivative of f of x, we get 4x cubed minus 12x squared, which is equal to 4x squared times x minus 3. We'll also need the second derivative. When we take the derivative again, we get 12x squared minus 24x, which is equal to 12x times x minus 2. Now we need to do what we've been doing. We need to find the critical numbers. To get that, we set the derivative, the first derivative, equal to 0. So we get 0 equals 4x squared times x minus 3, which gives us that x equals 0 or x equals 3. Now for the new stuff. Now we need to plug those critical numbers into our second derivative to use the second derivative test. When we plug in 0, we get 0. When we plug in 3, we get 36. See you in class tomorrow.